Hello and welcome to another lecture in Administration of Operating Systems course. Today we will talk a little bit more about networking, basically both about the general concepts and about some more interesting servers that you can set up in operating systems such as Linux. I'm assuming that all of you are familiar with the general operation of network. I know that some of you have had a course about it already, and those who haven't will have similar courses in the future. But the general idea is that in the network, typically when we talk about network, we talk about the internet. There are some smaller networks that you can talk about as well. But in general, you have a number of sites and a number of machines at each site, and you want those machines to be able to communicate. And there is a number of devices that allow this kind of communication. Things like routers and so on, which direct the traffic in appropriate places, things like firewalls, which ensure that only the appropriate traffic gets connected. There are devices such as gateways, which connect different types of networks together, similarly wireless access points. And of course, you have actual computers, printers, and all the devices that are the endpoints of the communication. So on the physical side, when we are talking about networks, we are talking about collection of computers and other devices that are connected by communication channels so that it allows them to exchange data. But actually, from logical point of view, one of the most critical aspects of the networking is the concept of protocol. And protocol is basically rules for how digital messages should look like. And the goal is to define both syntax and semantics. So basically, what does it mean for a message to be well formed? What does it mean how the structure of the message should look like? That's the syntax part. But also, what should be the meaning of the message? So for any given message that you could send, the idea is that the meaning of the message, what should be achieved on the receiving side by this message, should also be defined. And in a lot of cases, there are also at least a little bit of synchronization rules. So you want to say in what order those messages should come, if there are any limitations on things like doing operations in parallel and so on. And the important thing is that the protocol has to be understood by both sides of the communication. And in some cases, also by some of the intermediate nodes. The idea is to build protocols in such a way that they form a hierarchy so that you can build more complex protocols on top of the simpler ones, and then only the end participants in the communication have to understand the high-level protocol, and all the intermediate nodes only need to understand the simpler basic ones that are used for actual exchange of data. But it doesn't always work like this, so there are some protocols for which you need support in various places of the network. Another very important aspect of the network is the addressing scheme. So you have to have a way of addressing your messages in such a way that they will reach appropriate computers, and that also includes the routing strategy. So based on an address, each device on the network has to know where to send this message in a local, on a local level. So obviously you want in the end to the message to reach the final recipient, but you don't want all the devices in the network to have to know all the possible addresses. So in a bigger networks, you really need some kind of hierarchical addressing scheme. And we have talked about security before in the course, but actually the security only becomes really interesting once you start talking about networked computers. If your computer is only accessible locally by people who you can verify and whom you can trust, then the security problems are much simpler. If you put your computer on the internet, where potentially everybody can access it, then a lot of new interesting problems arise. And there is a number of different network devices that operate on different levels. So one of the most important ones is routers, because those are the devices which are responsible for directing the traffic, for figuring out what way should a particular message go, but there is a lot of different kinds of devices on the network that all have to cooperate in order for communication to actually take place. And there are two major routing schemes that you can be using. One of them is called broadcast, where a message is simultaneously sent to everybody. And this is how it works, for example, in Ethernet networks. This is how it works in wireless networks. You are communicating over a particular shared medium, and all the communicating nodes have access to it. So as soon as a message is sent over this medium, it will be accessible to everybody. And then, based on, for example, addressing and/or contents of this message, some nodes may decide to keep it and present it to the user, and some nodes may decide that it's not for them, so they will just ignore it. But the important aspect is that all the nodes actually do receive the message. And the alternative is the unicast model, which is the point-to-point communication. So you have two nodes, and each message is sent from one of those nodes to the other one. And this is what is often used in setups with dedicated communication lines. So you have two computers connected by a single cable that only connects those two computers. That's how the communication will look like. And you are also often achieving unicast communication on a logical level by using different kinds of routing protocols. So your message will actually only reach the single recipient if you take into account who is actually going to act upon this message. So on the way, the message will be received by other devices as well, but on a logical level, those devices will not do anything to it other than just forward it somewhere else. And so we can think of them as not really receiving it. Now, again, if we start talking about security issues, then of course the fact that they receive the message, they are supposed to ignore it, but maybe they don't, becomes an important aspect. But if we are just talking about how the network is supposed to operate, then we can think of a network such as, for example, internet, as being primarily unicast. And those are two major ones, but there are some other routing schemes that you can think about. One of them is the multicast, when you send a single message to multiple recipients. And you can either do it kind of directly in practical way, just by making sure that there is a single message that reaches multiple recipients, but it's very often also just simulated using either broadcast or unicast, just by specifying that the recipient address of this message is a subset of the whole network. So it's not really broadcast because not everybody is supposed to receive this message, but there's also not unicast because there is more than one recipient. There is a scheme called anycast, where the message is delivered to the closest target. So this is something you would want to do, for example, for load balancing servers. You can have geocast, where the message is delivered to multiple recipients based on their geographical location. So this is what actually happens in wireless networks. You can think of wireless network as being a broadcast network on a logical perspective, but if you start going deeper into how it actually works, it can turn out that not everybody is in range with everybody else. So you have a slightly more complicated routing schemes. And connected to this is the idea of addressing. And again, there are two major kinds of addressing. You can have the physical address, which is for example, something like geographical location or the actual physical cable connection. And you typically think of it also the MAC address, which is the address that is assigned to a network interface controller. So for example, the network card in a particular machine by the manufacturer. Those are all physical addresses. They are tied to some physical entity. It could be actual location, it could be a device, but there is a one-to-one link between the physical address and some kind of object in the physical world. The alternative is to think about logical addresses, which are addresses that you consider from application point of view. So they are not tied strictly to any particular physical device. Those are just addresses that you use for message routing, and they can end up in different places depending on the number of things. And the most common of those is the IP address, which I think all of you have already seen IP addresses before. And those are logical addresses. The same address can be assigned to different devices in different places at different times. So this is not tied to any physical thing. But what IP addresses allow you to do is, due to their hierarchical structure, they make the routing much simpler. And also in practice, instead of using IP addresses, you often use DNS addresses. So instead of 4 numbers like those, you would say that you are interested in this particular web server. There are also different kinds of networks. So obviously internet is one thing. There is wide area network, local area networks. Those are the most commonly used. But you can also think about different granularity levels of the network. Sometimes it's interesting to consider what is the, for example, best protocol for a particular size of the network, and depending on what kind of usage of the data you are interested in. In general, there are the basic protocol that is used in networking is IP, Internet Protocol. It's not the only one. There are other ones, of course, as well, more specialized. But especially when we are talking about the internet, as the name suggests, this is the protocol of choice. And this is simple datagram transmission service, which mostly deals with routing. So the idea is this protocol can get piece of data from one machine to the other. That's the general idea. Now, IP itself just deals with connection between machines, not applications. And it's important to be able to do different kinds of application identification. So if I'm going to talk to, for example, hh.se web server, I have to make sure that this message reaches the web server and not, for example, email server or database server, which could also be operating on the same machine. So for this, we are using something called port numbers. So each machine also has a number of ports, and then operating system assigns each application a port number. And this addressing scheme is used in the higher level protocols, so either TCP or UDP protocols, where TCP is connection-based protocol, so you start by initiating a connection, and then you get reliable stream delivery service. So you get delivery guarantees. If there are problems with the connection, the sending will be the data will be retransmitted until it actually reaches the recipient. It also does flow control, so it makes sure that you are not sending data too fast, so fast that the receiving server cannot process it, and so on. And the UDP protocol is much simpler. It's a connectionless protocol, and it does the best effort service, where it just sends the data, and then it's up to application to ensure that the recipient has received it if it's sufficiently important. And the IP protocol, there are 2 versions of it. The by far most common is IP version 4, where each address length is 4 bytes, and it looks something like this. And it contains on the order of 4 billion addresses. And we are more or less running out of those. So for a number of years now, there have been initiatives for getting an upgrade to IP version 4, and it's called IP version 6, where the address length is now 16 bytes, so it's significantly longer. If you do the math, it's quite some number of addresses. It's a lot more than in IP versions 4. And the work on the protocol began in 92. The request for comments, which is kind of a de facto standard description for the internet, was released in 96. But even today, there is still not that much traffic that's using IP version 6. It's less than 3% according to Google. On the other hand, it's growing pretty fast because last year it was less than 1%. So there is definitely potential for this to become significant pretty soon. And when you talk about the addressing, there are two ways of doing it. One is so-called static addressing, where system administrator assigns IP address to every machine on the network. And potentially also some additional configurations, because you typically just IP address is not enough. You need to have things like gateway address, some kind of root information, DNS server to use, and so on. So this kind of network configuration is more than just the IP address. You typically just say that IP address is the most important one of those. But it's not something that you really want to be doing, especially for bigger networks. So there are different kinds of dynamic addressing, and by far the most common is dynamic host configuration protocol, where a new node, so when a computer boots up or when it becomes connected to the network, it broadcasts a request for information, and then server, DHCP server, responds with an address which is currently free from appropriate pool based on a number of criteria. We'll talk about it a little bit more later in the lecture. And if you think about how GNU Linux network configuration looks like, first of all, you have a number of devices, because you can have multiple network interfaces that are connected to a particular machine. So you have to have a way of distinguishing between them. And originally, they were available as special files. So there was /dev/eth0, for example, for first Ethernet interface, or /dev/wlan0 for first wireless connection, and so on. Now, in modern Linux systems, the device files are no longer there. So it's very likely that you will not have those kinds of device files in your system. But the same scheme of logical names is still used for configuration. You can use, for example, lshw command to find out what kind of network devices you have installed. You can try lspci depending on if it's a PCI device. And you can also use ifconfig command to find out what kind of devices are available. Those are some of the ways of figuring out what to configure. And then most of the distributions have different kinds of graphical tools for doing it, because in most cases you don't really care about all the details, you just want something simple. Now, if you have a more complicated setup, it's often still more flexible if you do the configuration by hand using appropriate configuration files. But for most of the simple, classical, typical setups, the graphical tools work pretty well. And if you want to do the configuration by hand, one of the files is etc network interfaces, where you specify information about each interface. So, for example, here is a specification that will be using DHCP for IP address, and the auto here states that ETH0 interface should be automatically enabled when you start the computer. And here is the configuration for the static IP address, where you specify IP address, the network mask, and the gateway. You also may want to look at, for example, a file called resolve-conf, which is the file for DNS server. So here is the IP address of the DNS server to use, and so on. And there is the if down and if up commands for, it's called bringing interface down, so disabling it and bring it in the back up. You can use the ifconfig command for doing a lot of the configuration. For example, if you don't want to make permanent changes, as in those files, but just want to reconfigure the network interface for current session, you can use the ifconfig like this. You can also use the root command to configure routing information, so change default gateway for a given interface, and so on. In case of wireless networks, it's typically slightly more complicated because in general, the drivers for wireless network interfaces are significantly more complicated than for example, Ethernet. So if you have a wired connection to your computer, then most Ethernet cards will have readily available Linux drivers. But if you have a wireless card, it can be a little bit more trickier because first of all, vendors are less likely to release specifications for those devices, and the drivers are actually much more complicated. In many cases, they are not as much functionality is built into hardware. They can be using CPU for more complicated processing. So one way of dealing with that is to use so-called service called NDIS wrapper, which is basically a wrapper around software drivers. So it implements Windows kernel and NDIS API, and it allows you to use binary drivers for Windows in Linux operating system. So it can be interesting to know if Linux by itself is not capable of working with your particular wireless card. This might be a solution worth looking into. And there is a number of utilities related to the network. For example, the ping utility allows you to send a particular message to a host, and then the host is supposed to respond to it, so you can check the connectivity. The traceroute protocol will print the route that packets take to reach a network host, so you can see where the data goes before it reaches the particular destination. There is dig utility for looking up DNS information, TCP dump, and netstat for some information about the traffic on the network. We have talked already about telnet, which can be either a virtual terminal network connection, but is probably more useful for testing various protocols. We have talked about FTP, we have talked about SSH. There is a number of simple text-based web browsers, which again can be useful in when looking at network problems and trying to figure out why things don't work. Or if you just want to check something really simple, you don't necessarily have to open a full browser to look at some of the web pages. There are also more complicated tools. So one example is the Tripwire, which is a pretty powerful intrusion detection system. So this is a system which looks at a number of different problems that can happen and can be used for security policy enforcement. So the idea is to bring together a lot of different information and try to detect when something goes wrong. So it's pretty powerful. It has both open source and commercial editions, and it works on the host level. So it both analyzes the network traffic and file system objects. So you can, for example, not only detect unauthorized connections, but you can also look for unwanted system changes. So when some files change while they shouldn't, and so on. When you think about different ways of using the network, so what kind of computing architecture you are interested in, there are two major ones. One is called client-server, where you have a node which provides a particular service and a different node that makes use of it. And what it allows you to have is a simpler architecture. So you have one server and you have pretty good control over it, and then you have a number of clients that connect to it. But the potential problem is that there is a single point of failure. So if your server stops working, then nobody can access any of the information anymore. The alternative way of doing things is so-called peer-to-peer communication, where each node acts as both client and server, and you can share resources without the need for one particular central server. So it allows work balance and fault tolerance in a little bit better, but you often have a number of inefficiencies which originate from the fact that you only have local views of all the information. There is nobody who sees the big picture. Everybody just knows about their local environment. Now, on a less general and more specific level, let's talk about the domain name system. So DNS, it's probably something all of you have used before, unless you are always working with direct IP addresses. But the idea is to have a database which maps from human-readable domains like hh.se to corresponding IP addresses. And you obviously want this database to be hierarchical and distributed. Nothing else would ever work for a system such as the internet. And it started with RFCs 1034 and 35. So RFC stands for request for comment, and this is how all or most of the internet standards gets published. So there is a description of the protocol, and it's called request for comments because people can comment on it, point out inefficiencies, problems, and so on. And after some time, if there are no more objections, people start actually implementing software that follows this protocol, and at some point it becomes a standard for the internet. Now, this was just the beginning. There is more than 50 others, RFCs, that describe various modifications and evolutions of the DNS protocol. So it's not as simple as it sounds. Now, originally in the ARPANET, there was just a file which listed all computer names and their IP addresses, and this file would get distributed periodically to all the computers on the network. Now, this worked fine for a couple hundred, maybe a couple thousand computers, but at some point it obviously didn't scale well enough. So there was a need for something better. So DNS is an application level protocol. It uses TCP or UDP, and originally it didn't have any kind of encryption. Now DNSSEC, the secure version of it, is becoming popular. Not necessarily on the end user level, but on the higher levels of the internet hierarchy. It's used more and more often. And one of the most popular implementations of the DNS protocol is the bind9 server, which has configuration file called named.conf. And the idea of DNS hierarchy is something that probably everybody knows. There is a number of top-level domains, so those could be like com, edu, gov, and so on, and then for different countries. And each of the domains is registered in a superior domain. So you have a tree-like structure, and then each domain can manage its own subdomains. And the structure of the DNS hierarchy tree is very similar to how the file system looks. There is a single root, and then you can have absolute and relative paths. The major difference is that you start writing it from the right instead of from the left. So the root is here, and you typically, when you are typing address in your, for example, web browser, you skip this final dot because the web browser is assuming that what you are giving it is the absolute path. But there are contexts in which you can also use relative paths. For example, when configuring the bind9 server, you will often be using in different places the relative paths. So it's important to know the distinction. So on the right, you'll start with the root domain, then you have the top level domain, then separation. In this case, they are obviously separated by dots, not by slashes. Then you have second level domain, some kind of subdomain or host name, and it can go on basically however deep you really want to go. And within the DNS service, there is a number of different so-called resource records. So there are different pieces of information that are associated with each particular domain. And for representing different kinds of informations, you have different types of resource records. So for each record, you typically have a domain. You have the class, which is almost always in, which stands for internet. But, well, DNS predates the popularity of internet. When it was designed, there were different kinds of networks that you could be using. And then there is a type of the record and different kinds of values. So one of the primary records is so-called start of authority record, which is something that has to be created once for each domain, and it contains some global information about a particular domain. So for example, it contains information about time to live. So how long do you want the information in this particular record to be kept in the cache of other servers. So the idea is that if the information is changing often, then we want this time to live to be short, so that it will be requested from the real source pretty often, but that means that there will be more traffic. So if your data is not changing very often, then you want to set this to a larger value so that you will get less requests, because people will remember it, or systems will remember it in their cache. There is a serial number which can be used for up-to-date tracking. So instead of requesting all the data again, you can just request what's the current serial number and compare it to the data you already have in cache. If it hasn't changed, then you don't have to transfer all the information. And it contains the authoritative name server, so the name server which knows all the true information about the particular domain. So that's the one who is responsible for providing it. And also things like admin email address and so on, just in case. There are other types of records. So one of the most common ones are the address records. So you can have IP version 4 or IP version 6 address. There is a CNAME type, which stands for canonical name, and it is useful for hostname aliasing. So when you have a computer which have multiple different names, then this is the kind of record that you would use to specify this, that for example www.he.se is a alias for a different kind of, for a particular kind of machine. You can specify email servers, name servers. You have pointer records which allow you to do reverse DNS queries. So basically asking what's the name for this particular IP address. You can add some additional text information, and then there is a number of different types for security related information. And basically, from the client perspective, what you are most often asking is the IP address. And as I said, you can have several of those, and you can configure your DNS server to, for example, cycle through them. So you may have several web servers for hh.se. Now, our web page is not big enough. We don't have enough hits to really require it, but bigger servers sometimes have duplication. And you can use DNS as a very simple load balancing mechanism, where every time a client requests the IP address, you will get a different one from a given pool. Here is also some again information about what different kinds of service records mean. Here is an example of a particular configuration for a DNS record, so you can take a look at it. And the important concept is the concept of zone. So DNS space is divided into zones, where each zone is administered by the single DNS server. So it doesn't have to be one domain. One DNS server can administer multiple domains, assuming they are related, because otherwise it doesn't make much sense. Now, obviously, the main reason for having DNS system is to be able to answer queries. So there are a couple of different ways in which a server can answer a query. The easiest one is when DNS server receives a query about its own domain. And then it will answer with what is called authoritative record. So it will tell, this is the IP address for the computer you are looking for, and I'm sure of it because that's my computer. I'm the one who has the real information. Now, if it receives a question about a different domain, it may still provide answers if this particular data is in cache. That's called non-authoritative response, and basically it means that I'm not the one responsible for this data, but I happen to know it, so here it is. And that can happen on all levels of the hierarchy. So both the top-level domain servers and any other kind of server can also provide non-authoritative responses. And then, if the server doesn't know the answer, it can either make so-called recursive query, where the server will contact the the name server that might know, wait for the response, and then give the answer to the client. And this will usually start with the name server for the top-level domain, and it will continue the requests down the hierarchy until one of the servers will actually provide the answer. Or it can do the iterative query, which will basically tell the client that I don't know the answer, but here is the IP address for the server to ask. So the iterative query is less work for server, more work for client, and which one you want to implement basically depends on where in the hierarchy you are. The top-level servers almost always do iterative queries because they have enough traffic already. And the servers, for example, in internet service providers, they will typically do recursive query because they want to know the answer as well, so that next time some other customer wants to know the same IP address, they will be able to provide it faster and without any outgoing traffic. So here is a picture of how it can work in practice. But there is one problem with this kind of approach, and that's because authoritative name servers are usually located within the domains that they operate. And there can be some circular dependencies with this. Because if I, for example, ask DNS server what's the IP address of www.foo, then I might get an answer, ask ns.foo about all the addresses in the foo domain. But how am I going to find out the IP address of this guy? He is responsible for all addresses in the foo domain, but I don't know his IP address. So in such cases, when name server is providing the records, they also need to add more information, in particular the IP addresses for authoritative name servers. So whenever a DNS server will tell me ask nsfoo about IP addresses in .foo domain, it will also tell, and by the way, the IP address for nsfoo is something like this. So this is important to remember. And originally DNS protocol was all unencrypted, but it turns out that there is actually a need for a little bit more security in here. And so each DNS zone has a public and private key pair, so pretty similar to what we talked about in SSH. And then all information from a DNS server will be signed with appropriate private key so that the client can verify its authenticity. So the main goal here is to provide guarantees about origin of the data. And also the protocol itself helps in distribution of public keys, guarantees atomicity of transactions and authentication the requests, but those are all secondary issues. Now, there is no confidentiality service in here. All the information is public anyway, so it's not about eavesdropping on the traffic. It's all about making sure that the data you are receiving as a client can actually be trusted. Because something called DNS spoofing is pretty easy to do and very dangerous. So Trudy can try to convince Alice that Bob's IP address is this one instead of this one. This is something that can be easily done and is a significant security problem. So since DNS, especially by default, uses UDP, the server has no way of knowing who supplied an answer, so it's really easy to provide fake answers, and here is how the scenario could look out. And it's slightly more complicated than that because typically DNS requests carry so-called sequence numbers, so the response has to match this sequence number, but even then it's not that difficult for Trudy to try to guess this sequence number, even if it doesn't really eavesdrop on the traffic. So the idea behind DNSSEC is to combine all DNS records into units which are called resource record set. And then you can sign this as a whole with zone's private key. And then since the whole record is signed, it can be cached even at untrustworthy servers. You really want to be able to cache this information at servers which don't have private keys for a particular zone. Because one of the major concepts behind DNS is that there is a lot of caching going on, so you don't have to be asking each server every time about the IP addresses. And the important design concept in DNSSEC is to be able to do all the actual encryption offline. So you only need to encrypt information when something changes, when new records need to be signed. And this can be done on a machine which is not connected to the network, thus increasing the security significantly. And it's crucial because if you could leak the key for one of the top-level domains, it would break the whole system. It's also nice for speeding up operation because those cryptographic operations are reasonably slow, especially compared to simple lookup data. And if you think about how many requests a server responsible, for example, for .com domain gets, it's important that it can operate efficiently. So there is a number of additional record types which are related to security, so things like key or SIG. But the most important aspect is, a more interesting one, is how to deal with domain does not exist message. Because such a message would not be safe against replay attacks if all the cryptography has to be done offline. So, because then somebody could just fake this kind of response just by storing it when it was given to him and then showing it to somebody else, even though the somebody else is asking for a domain that actually does exist. So it's not possible to pre-sign all possibilities because you can't figure out all the names that the clients could be asking about. So you can't say that A.com does not exist, B.com does not exist, and so on. All possibilities, that's way too many to sign. So originally what was introduced was so-called NSEC response, which said basically that there are no hosts alphabetically between A.com and B.com. And that was good enough. That was a valid answer that you can provide. And then the client can verify that if he is asking about ABCD, then okay, that kind of host doesn't exist. If he is asking about host called C.com and gets this kind of this answer, it cannot come from the real host. It must be an attack because it doesn't really answer the question that he was asking about. Now the problem with this is that it makes zone enumeration very easy, so it's very easy to get a list of all computers in a particular zone, which is something that you don't really want. So that was partially fixed with a more complicated NSEC-free protocol. And the idea of operation for DNS Secure is that clients already have the public keys for the top-level domains. And then when Alice asks, for example, the com DNS server for RRS set corresponding to bob.com domain, it will contain DNS server IP address and zone's public key. This will be signed, so it can be trusted. There is no way for an attacker to forge it. And since now Alice has the public key, it can securely get information directly from Bob's DNS server. And as I mentioned, the most commonly used DNS server is Bind9. It's basically a de facto standard for the internet. It has a history of security vulnerabilities and a very complex configuration, but it has a number of interesting features, and if you need something very flexible, it's probably still the best one. There are other alternatives which are much simpler for most common cases, but typically don't have all the functionality of Bind9. And there is a number of interesting options that you can use in here. One of the most important ones is so-called views, where you can specify that the responses that server gives to clients from the internet will be different than the responses it gives to servers from the local network, which can be very useful. Another service that is interesting and worth talking about is the network information servers. So the idea is that you want to have a system for distributing configuration data, user and password information, and similar things across a number of computers in the network. So it was originally developed by Sun Microsystems for their Solaris operating system, and the idea is to simplify maintenance by keeping information in one place and then distributing it across a network for a lot of other machines, so to make network environment more transparent. And the idea is similar to what is currently called Active Directory in the Windows world, for example. Because if you think about how local administration looks, you have, for example, list of usernames in etc password file, and users are created by user command, which basically just adds new lines to this file. And similarly, users can change this data using, for example, passwd and so on. And this all just corresponds to modification of those files. Now, if you have a network environment, this will not work anymore, because users definitely don't want to remember, for example, different passwords for different computers, or if you have already updated a password on this particular machine, and you don't want your administrators to need to update the configurations in multiple places, for example, on all the workstations and so on. So you want one local place where you do it. And you can use NIS server for that. And NIS server allows you to have a number of so-called maps, which can be useful, for example, for roaming profiles and passwords. Those are files which are indexed for efficient access. So you can have, for example, passwd by name and passwd by user ID files, and those contain the same information. It's just that in this one, it's easy to find information given a particular username, and in here, it's fast to find information by user ID. And the system was originally called Yellow Pages, but it actually is a registered trademark of British Telecom, so it has to be changed. So now it's called NIS, but there are still some files are called YP something, so you will see it in a second. And NIS is based on the concept of domains. So each domain has a name, and there is exactly one master server for it. There can be a number of slave servers. While one server can serve multiple domains, each client will belong to one domain at a time. But it's easy to move between domains. So for example, you can use the work versus home setup using NIS servers. The traffic is not encrypted by default. It only has weak security model, which is basically based on IP addresses. So you can specify from which hosts which hosts should be able to access the information and which are not. Finally, most modern Linux distributions allow you to specify in what order and where do you want to search for this kind of information, most typically using something called name service switch, which lists the sources of information and their lookup order. So you can say, for example, that for information about users, you should start by checking the local files, and if there is no information there, go to the NIS server. And for list of trusted hosts, you should start with local files, then go to LDAP, then check the DNS information, and so on, which is very useful when you want to combine different aspects. So for example, you want to maintain part of the information locally, but some kind of more global information you want to have in one central place. The installation of NIS client and NIS server is pretty straightforward. Of course, one machine can be running both if you want to. Now, from the client perspective, you want to pay attention to some things. So first of all, in the configuration file, you can either specify the address of NIS server or use a broadcast mode. and you typically want to have the address of the server. The broadcast mode is very, very insecure, so this is something you probably want to avoid. You want to make sure that passwd command does the correct thing for your users, because by default passwd command just changes local files. If you want to be updating the NIS server, you should be using yp passwd. This is where the yellow pages comes from, and you really want to make sure that your users don't have to remember this distinction. A more modern version of NIS is something called LDAP. It's significantly improved, for example, as far as security goes. It's a lot more complicated, but it allows you to have a directory of arbitrary data, where you can have each directory entry consists of a set of attributes. It has name and a value, and then you have a schema which defines what kind of attributes should be there, what kind of attributes have to be there, what are the ranges for values of the parameters, and so on. So this is much more complicated, but it allows you a significantly higher flexibility as to what kind of information you can store. And in general, it's just a specialized database which is highly optimized for reading and searching, and much less so for updates, but that's how you typically want to be using this. And it can store arbitrary data, so you can store passwords, phone numbers, JPEG photos, anything you want. Here is how the hierarchy can look like. So LDAP is always hierarchical. You have different objects and different levels of the hierarchy, and those objects each have a distinguished name. So there is a full name of each object, and typically it's hierarchical, so you just describe the path to reach a particular object. And then for each attribute, you can have one or more values, and you specify different types for those attributes. And there is a object class attribute which decides what other attributes should be there, or which are required and allowed for a particular entries. So you can say that, for example, each person has to have a name, phone number, and a room number, while, for example, a department cannot have a phone number, and so on. And the schema allows you to define what kind of data is stored at different levels of the hierarchy, and it helps maintain consistency and quality of data. So that's pretty interesting. You can, as I mentioned, say what are the required, what are the allowed attributes. You can say how to compare attributes, what are the types of attributes, what's the structure of the hierarchy. So you can say that, for example, each department has to have one leader and a number of employees within the department, and so on. All those things you can define. And then there is a number of already publicly available schemas for various kinds of directories. So, for example, for a company and so on, you can find existing schema, which probably will do more or less what you need anyway. If you are talking specifically about authentication users, one possibility, as we mentioned before, is to have passwords in a centralized place, but you can do something also significantly more powerful. There is a service called pluggable authentication modules, which again was proposed by Sun Microsystems in the 90s. And the idea is to have a centralized authentication mechanism, which doesn't necessarily is based on passwords. You want to have an abstract way which will allow you to plug in different authentication methods depending on different set of criteria. So you can have different authentication methods, for example, for different users, or different access methods during work hours than during evenings or at nights, and so on. There are a lot of modules available capturing different kinds of authentication methods, and it's very flexible how you can combine those. If you are interested in a distributed authentication protocol, so if you have a network in which there is a number of workstations and a number of servers, and you want to be able to ensure that users can authenticate to servers in a secure way, then there is a number of distributed protocols. Kerberos is probably the most commonly one the one that's most commonly used in practice. And the idea is to allow the user authenticate to the servers without sending their actual passwords at any time. So there is a special entity called authentication server, and this is the one that shares a secret password with every user. So this is the server on which each user has their password. And the idea is that Alice trusts AS with her password, but doesn't want to send it over the network, and especially doesn't want to send it to any other server. So the idea of Kerberos is that we want to have Alice only authenticate herself to the authentication server, and then this server is supposed to vouch for her to everybody else who wants to verify her identity. So in particular, when Alice sits at the workstation will send the username to the server in plain text, and then server will send a session key and a ticket which is encrypted using Alice's secret key. Workstation will ask Alice for password, decrypt the session key and the ticket, and then immediately delete Alice's password from memory. But that's enough to verify that Alice really knew it, because if the decryption here is successful, then Workstation can be sure that Alice is really who she is supposed to be. And that also works for other servers. So you can have a ticket granting server which will grant tickets allowing Alice to communicate with, for example, Bob, without actually Alice ever sending her password over the network directly to Bob. Here is again how this kind of communication can work. And the idea is that you don't ever have to show your password to any of the servers, never send it through the network to anyone. The only time when the password is vulnerable is a few milliseconds on the workstation while the workstation is using it to decrypt the session key. So this is a pretty secure scheme. It's very complicated, both in concept and in actual administration. But if you have a large network with multiple levels of trust, this is probably the best option out there. And the final service I wanted to talk about today is email, and I'm assuming most of you have used it before. But what is interesting about email is that this is an asynchronous protocol. So you have your user who is writing the email, you have user's server who is waiting and will then transmit this email to the recipient's email server, and you have the recipient. All those agents can be doing different things. And whenever Alice is ready with the message, she will send it to her own server and kind of forget about it. Then Alice's email server will at some point send it to Bob's email server without involving Alice at all. And then Bob's email server will at some point pass this message to Bob without involving Alice or Alice's SMTP server at all. So this is different protocol than, for example, FTP or SSH, because now you have different servers who cooperate in sending the message, but they don't synchronize it among themselves. So it's kind of a send and forget idea, and you trust the servers on the way to do their job or to send you a message back if something doesn't work. And in order for this kind of infrastructure to be viable, it requires a number of different agents. So the most obvious one is mail user agent. So this is the email program that you are often interacting with, and there is a number of options. The next step is the mail submission agent. So this is actually the agent which takes an email and talks to the server that it should be delivered to somebody. And those two things are often combined. So Almost all user agents actually contain the submission agent functionality as well. But there are situations in which those two things can be separate. When you have, for example, a multi-user server which also acts as the mail server, then it might be enough to just save the email message somewhere and then it will be picked up by the email server automatically and so on. The next step is the mail transfer agent. So this is the actual server. So this is the program which will take the email, try to find out to whom should it be sent. Based on the email address, try to find the server to which it should be delivered. And there, again, there is a number of different options here that you can choose from. Fine. On the other side, and it typically can happen that there will be multiple mail transfer agents involved in sending a particular email. In most cases, the agent is trying to directly deliver it to the mail server that belongs to the user who is the recipient of the message, but it's actually possible to transfer the message in a number of steps via multiple transfer agents. Once the message reaches the final step, there will be agent called mail delivery agent or mail retriever agent. Basically, depending how your mail system is organized, it can be mail delivery agent is the agent which works on the server side, and whenever a message arrives, it places it in an appropriate place so that the user can find it. And it often works in, for example, Linux-based systems, that there is a special directory where all the mail messages end up, and the mail delivery agent can just put messages in this directory. So this is kind of a push paradigm, where whenever the message arrives, there is a special agent which takes it and places it in the location where the user can find it. The alternative way of doing it is to use mail retrieval agent, where once the message reaches the final MTA, it will stay there and it will wait until the user actively connects to the server and tries to retrieve the agent. So you may have a service in which your mail agent, user mail agent, connects to the server periodically and asks, are there any new email messages for me? So here is an example of how it can work. And again, the exact distribution of which parts of this functionality go into which software tool are somewhat flexible. But basically what you want your mail user agent to do is to be able to allow you to compose email, read email, send email to own server, not necessarily to any other server. You want to have your own server, and the user agent is only supposed to be sending email to this agent. Receive email from your own server, and the idea is that this is the tool which is on and off. So you connect to a network, you send your messages, you disconnect from the network, you can still read them, you can compose new messages, and then when you connect again, those will be sent and new ones will be received. And on the other end of the spectrum, there is an email server, where the idea is that it receives emails from the users, it will forward it to their destination, it will gather email for users, so when new messages arrive and the user is offline, then the server will store it for later. It often does additional services, so you can have things like mailing lists and so on. And the idea is that this part of the infrastructure is always on. So this one is always ready to receive new messages. And again, here is the life cycle of an email in a sense, where you start by composing a message, then sending it to own mail server, then the two servers will talk, either directly or maybe there might be some intermediate server in between. The message will go from one to the other, and then Bob will receive this message and invoke his user agent and read the email. And again, the start and end of this can be done offline, and then all the middle is done by the servers. That's the general idea. Now, the most interesting thing is that the difference between mail submission agent and mail transfer agent is basically very, very thin, because what MTA does is exactly the same thing as MSA. It just sends a message from, it has a message and it wants to send it to a different server. Now, there are some benefits of distinguishing between the two. There are some which are security related, but the important thing is that you know that the mail submission agent is talking directly to author's user agent. And so it can correct some minor errors in the message format. So for example, if there is missing date or missing message ID field, the MSA can just fill those in because it knows the message is being sent right now, so I know what the date is. If it's a MTA that receives the message without the date, it doesn't know how long the message has been in transfer, so it can't really fill this field in. And also, some of the errors, if they can be immediately reported to the author, then it becomes easier to correct them before the message is sent to any recipients. So for example, if you are sending an email to multiple users, and one of those users does not exist, if you are talking to MTA, the MTA will just have to send the message to all the recipients it can and give you back error information that one of the recipients was not available. But if it's MSA, then it can just say, well, one of the recipients is not available. I will not send this message right now. Fix this problem and try again. Now, the reason why MTA cannot do this is because MTA never knows if it has the full list of recipients, because the message might have already been sent to some users. And then the idea is you want to send it to as many recipients as possible and just ignore those that don't work. But if you know that you are the first step in the process of sending it, then if you know that the message has not yet been sent to anybody, then you can immediately give the feedback to the author and make sure that those problems are fixed before the message is sent to anybody. There is a number of email protocols. The three most common ones are SMTP, which is for sending email, POP3, which is basically for downloading email, and IMAP for accessing emails on the server. So here is a short example of how SMTP communication can work. And again, this is something that can be done using specialized email clients, of course, but you can also just fake it using Telnet. All email messages, besides the body which contains the actual message, they also have a number of headers. And the only two which are actually required are from and to headers. So you have to say from whom the message originates and where should it be delivered. Everything else is optional. So fields like subject, CC, in reply to, those are examples of headers which are optional, but a lot of the time they are useful. And then there is a number of headers which are added automatically, like date, received, message ID, and so on. And one of the headers is about type of the contents for the message, because initially it of course text that was being sent via email, but at some point people have noticed that there can be sometimes other things that you want to be sending, and then you want to tell the user agent how the data should be presented to the user. So the multi-purpose internet mail extensions is the description of the contents in such a way that the different kinds of agents can display it appropriately. And you can, for example, have a message which consists of multiple parts, and then you can specify that either this is multiple different parts which should be mixed. So there are, for example, some text followed by some picture, followed by more text, or you can specify that there is multiple alternative ways of displaying the same content. So then the agent should choose which way of displaying the contents should it employ. And there is also the content transfer encoding header, which specifies how the data should be encoded, because SMTP protocol, it just expects standard ASCII text. So binary data has to be encoded in some way. And for different kinds of contents, there are defined a number of so-called MIME types, where you specify what kind of content it is, and then a more specific description of the details. So for example, you can say that this is a text content, and then there are different kinds of text. It can be plain text, it can be HTML or something else. And you can say that it's an image, and then different kinds of image compression formats, and so on. Here is an example of how that kind of message might look like. So you have multiple alternative content type here, and so you can choose either text enriched or audio contents, depending how you want to present the happy birthday song. And for accessing email, there are two major protocols. One is called POP3, Post Office Protocol version 3, which allows you to do the basic things, for example, authorization, listing messages, retrieving messages, and so on. And the idea here is that the user will download the messages to his or her computers and then manage them over there. A newer and more complex protocol is called IMAP, where the idea is to keep messages on the server in some kind of folder hierarchy and so on, and then just synchronize the data between server and the cache that's maintained by the client, but the actual contents stays on the server. And then more and more popular is the webmail access, where the ideas are kind of similar to IMAP, except instead of having a client on the user side, you only have the web page which uses this kind of aspect. And the benefit is that there is more functionality. So it's an actual application, not a protocol. So the authors can do whatever they want. And it has all the usual features of web applications, so both advantages and disadvantages of those. And one example of server that can be used for managing emails is, for example, Exim4. So the thing to remember is that you only need this kind of server if you have your own domain where you actually want to receive the email. In most cases, you are just interested in having a client. You don't need email server. But if you do, you can install, for example, Exim4, and it can be configured in a number of different ways, depending on what kind of functionality you actually want. It's also pretty common that you have some users on your system which are not real users, and the emails that are directed to them should be forwarded to somebody else. So for example, webmaster, tech support, root, and so on. And you can use, for example, a file called etc aliases for doing that, or you can use .forward file for similar purposes. So this can be used as a very simple form of mailing list. The actual software for managing mailing lists offers additional features, but if you just want to have, for example, all email which is sent to the admin user forwarded to those two addresses, etc aliases might be enough. And that's just the beginning. There is a lot more software which is related to email. There is various spam removal software, for example, Spam Assassin. There are different kinds of mail servers and clients. There is a Mailman for managing mailing lists and so on. Now, what I wanted to close with today is a description or a way of looking at configuration files. You have already worked with different configurations files, for example, for SSH server. And it's important to be aware of there are different kinds of configuration files. They all have some kind of structure, but the structure can be very different. So here is an example of configuration file from the HCP server. And as you can see, there is some number of kind of global options, and then there are different groups of options where you specify for this particular subnet, here this parentheses means that all those options inside, they will apply to this particular subnet, and you can have another subnet outside of it. And similarly, you can often nest those kinds of sections. So now you have a host, and for this host, again, you are using the square brackets to say that those two lines apply to this particular section. In a different file which you have worked with, in the Samba file, you also have sections, but the configuration file looks completely different. And in here, the sections are defined using square brackets, and then everything that's inside here will apply to this particular section. A simpler file like SSHD, there are no sections here. Each line is one option, one value. So it's the name of the option and then the value, and that's it. This one is much simpler. For a bind server, the configuration is even more complicated, but again, it follows a very similar structure. You have those brackets which define different sections, and you specify what belongs to each section. And again, in Apache, which we will be talking about in a week, the structure is again different. This one follows more something similar to XML protocol, where you have sections which are defined using this kind of syntax, and then the section is closed using the slash character. So here is the beginning of the section, and here is the end of the corresponding section. Here is the beginning of the section, here is the end of the corresponding section. And again, those things can be nested. So it's important to remember that all the files have particular structure. You have to figure out what kind of structure this concrete file is using. There is no agreement between people who create this software as to what is the best structure for a file. And it also very often depends on how the configuration files actually look like. But when you are faced with a new configuration file, typically there is some reasonable idea behind how the file looks like. So it's important to start by figuring out, so what are those things actually mean, and then start looking at individual options and trying to figure out which of those you are interested in changing. So thank you very much for today, and I will see you on the lecture.